So now the series of slides begins, which basically aim to explain what you really see in a more practical way. First part is about organic samples. So I'm sure if we ask 5 people here what is organic material, we get 4 different answers. Because there's life science, for example, cells, viruses. These are all life science applications. We could ask a material scientist. He will think of polymers maybe, conjugated polymers, rubber materials. Some people may think of organic semiconductors. So there's a big group of materials which fall into this category of organic materials. And I will start with some basics. First, you don't have to take my word for granted. You can also look at this literatures here. Especially, it makes sense to know the work from Florian Hood if you are doing nano-FTIR from IBAN, specifically for organic samples. It's a very good resource. Also, there's a PhD thesis from Stefan Mastel. It's very useful paper for thin films. For subsurface material, you would look at my paper. And then 2 more where we have separate talks later. And I always like to advertise my PhD thesis because I put a lot of effort into trying to put many details into the introductory chapters while being easy to understand, but not losing too many details. And then maybe you can have a look. You can download it here. And the goal of this talk is basically to explain this figure that we've seen already several times. The way we will do it is not via slides, but via like an interactive simulation, which we will do a bit later. So if you have any questions, if you want to change any, so ideally I would like to make an experiment with you, because that's how you learn the best. But we cannot do it here, so we simulate. And we can play around with this. So keep this in mind. And the nice thing is, for the first part, we talk about organic samples. All we have to really care about is this weak oscillator term. And we can see already the permittivity and the s-SNOM signal, they somehow look the same. And I hope I will be able to explain why. And what are these weak oscillators? If you have a polymer, for example, PMMA, you can write down the structure formula and see their individual bonds. And this vibration is just really a vibration of this bond. If you look closely, first of all, you see it's the wrong molecule. And second of all, it's not only these 2 atoms moving, but it's also the whole structure of the molecule vibrating. So it's very complex what information is in one of these bands. But it's easy then how it looks in the s-SNOM. So molecular vibration is a weak oscillator. And each organic material, they don't have one of this, but they have many of them. They have several tens of them. And all of them, they have a different peak position, they have a different line width and relative height to each other. And this is all full of information. This all can tell us something about the sample. And the important thing here is this is described with permittivity or reflective index. We have a real part, imaginary part, and they contain the same information, let's say. So every peak that you see here in the imaginary part or in the absorption, you can see also in the real part. And you can assign this to 2 different modes, compare with the infrared database. There are different types of vibrations. Sometimes it's important. I will show later an example what they are. In general, it depends on your research if this is important or not. But importantly, if you have all these peaks, you know what material you have. And even more, you know if it's degraded, you know if it's chemically interacting, things like this. So the experienced people already know if they see these type of peaks, they would identify even without any computer that this is PMMA. But we have computers, so you do have the option to use a far-field infrared spectral database, which contains a lot of different spectra. And you can compare this with nano-FTIR phase spectra in this case. and the computer will tell you what is the most probable match of this spectrum. So in this case, the computer will tell us this red spectrum, nano-FTIR spectrum, belongs to polyamide. And it has a hit quality of 797, whatever this means. But it's the largest number in this. So there are different ways how you can do this. There are open source libraries. But this is possible, is what some people are doing already. And the reason that we can do this, that we can use a far-field database and compare it with a near-field spectrum, is that we are dealing with weak oscillators, and they are relatively easy to interpret. Because if you look here at the permittivity and the far-field reflection and the absorption, it's essentially the same. Yeah, 5 minutes? Good. And now, very good for us, if you do the same with the near-field, it's still the same. So the near-field phase is roughly imaginary part, or the absorption, and for the reflection is correspondingly. And this is now shown here from the first nano-FTIR paper from Florian Hood. There's this nano-FTIR spectrum, which is showing the peaks. Actually, we record also the reflectivity spectrum, so I asked Florian to find the data, which he did. And we can see, indeed, all the peaks, they also have in the amplitude a signal. What I want to say here is, yes, you can use this phase to identify the material, but nothing's stopping you from using also the amplitude. Yeah, and the reason why this works, this is shown here in a complicated graph. This is the s-SNOM amplitude as function of sample permittivity. And we can see on the left-hand side, we have this around epsilon -1, -2, a very sharp resonance. This happens only for organic samples, typically. This will be after lunch, we talk about this. And here we talk about organic samples, and it's more or less a linear relation. So for every value of permittivity, we have a clear point on the amplitude. So it's almost one-to-one correspondence of the permittivity and the near-field amplitude. And the same is for the refractive index. So it's the same graph, just plotted as function of refractive index. It's linear, so wherever we are, we can almost from this determine the refractive index. So that's why these samples are relatively easy. And how much time is left?
3 minutes.
3 minutes, okay. I can show some first basic examples. So this is now a blend of two polymers measured in the visible range. The refractive index is different. It's 1.5 and 1.6. And we see an optical contrast here, which I interpret, it's not peer-reviewed, I interpret this as having a higher reflectivity here due to the refractive index. And this is the kind of sensitivity that we get. So, so we can distinguish materials. From this data, we don't know what material is what. But this can also be done. So here from Thomas, actually, is an old paper with a PMMA layer on a silicon substrate. And we can see for different infrared wavelengths or frequencies, the contrast changes. And we can do this for many different frequencies, and we can track really nicely this dispersive shape that we've seen before. So it's just going up and down here. And this is now the spectral fingerprint of the CO vibration in this case. So with this measurement, we can chemically identify the PMMA. And this is not nano-FTIR phase or anything like this, it's just an amplitude. And you can still do this. And I just wanted to mention it here because some people forget sometimes about the amplitude. It's useful too. And in this case, this is also modeled. The black curve is modeled for infinitely thick layer of PMMA. In the experiment, we can see the amplitude is a bit brighter, and this is because we have a film on a very bright substrate. And we start seeing here the substrate. And at the time, there was not yet the layer models. Okay, and then the last slide before lunch is the same principle, but now we have an unknown sample. It's a polymer blend. We could take an image at the frequency where we expect no contrast, and indeed, there's no contrast between the matrix and the spheres. But we tune a bit the laser to this frequency. We can see the PMMA, so orange is PMMA. This is now bright. And at this wavelength, we can see the film is now dark. So we know from these three images that this film is PMMA and the spheres are polystyrene. Here is first an example from IBAN on an insulin fibril, I think, yeah. And we can see on the right side, this image, nothing absorbs in the sample. That's why there's no phase contrast. And then tuning to the laser to a different wavelength, we can go onto the amide band and nicely highlight the areas where do we have protein in the sample. So this is now chemical identification via near-field phase. And this was one point that was already shown a few times, but not explicitly mentioned, is that you can take a spectrum also with a series of images. So you don't take 2 images, but you take 10, like shown here. And you can map the spectrum. It's a very tedious experiment, but before there was a nano-FTIR laser, that's what you had to do. And the nice thing is, if you now have the nano-FTIR laser, it's much easier. Of course, you get only 1 pixel, but the spectra, they nicely overlap. So they contain, in principle, the same information, and if you keep all experimental settings and parameters the same, you also get the same number. So let's say this is 50 degree high. It doesn't depend what laser you use. You should get a contrast of 50 degrees, which then also can be described by a model. So what I prepared here was is a finite dipole model calculation using the model for the infinitely large sample. And it's based on defining this dielectric function. So this is our material. And then I plot next to it the calculated nano-FTIR spectrum, amplitude and phase, and also the expected s-SNOM image in amplitude and phase. And now we can play around with this. And I'm also open to suggestions, what we can play around with. So just to demonstrate what we can do, we can, for example, move the, one thing I forgot. This dashed line, it shows at which frequency that image is taken. So the first thing we can vary is the imaging frequency. Now I hope this will work. This is grayed out. I think I have to run the notebook. It will take a few seconds. And now, hopefully, if I can click here. Yeah, the wavelengths that we're using now in our experiment, we changed it. The contrast is now turned off in the phase. So we can see it's not absorbing. There's no contrast. But in the amplitude, there is a contrast. Does this mean now that this material here is somehow, are we chemically probing this material? No, not really, because it's just a silicon substrate. And we have here a sample, biological sample, organic sample, where the refractive index is normally quite low, and that's why it's appearing dark. And it doesn't matter, or rarely matters, which frequency we use. The amplitude image is always the same. Yeah, so this, if we look on this scale, we don't learn something from the amplitude. But I've shown before, if you zoom in and you really quantify, you do see a difference. And maybe if I hit the peak just right, so now the upper image here, it's really, really dark, because we're here in the minimum, and also of the dielectric function, we're in the minimum. And if we go a little bit to the left, I don't know if the beamer has shown this, but this is now a little bit brighter. And also the number is a bit bigger. Yeah, but that's probably the reason why we don't look at the s-SNOM images, at the amplitude images, because it's really hard to tell what's going on. Whereas here in this phase image, it's a very clear contrast. So it's much easier to interpret. Yeah, so for organic samples, it's not so interesting to play around with this. But in a few minutes, we play around with this for stronger oscillators. We can make it also broader, all these things. And you see that the shape is always the same. Yeah, what you also see, if we tune exactly to the maximum here, we can see that the laser is now tuned to the maximum of the imaginary part of dielectric function, But in nano-FTIR, we are a little bit off. So the peak position is slightly shifted by a few wave numbers. And this is now the next part of the talk. I want to talk about this kind of shifts. So we go back into the slides. Yeah, this is also now animation, just sweeping the laser. We can nicely see it's absorbing. Now we are off the absorption. Okay. Yeah, so this doesn't match. And then the question is it a problem that these peak positions don't match? I would say that no, it is not, because in the far field it doesn't match either. And it hasn't stopped far field spectroscopy from being successful. So now we're starting to talk more about the details of spectroscopy. And in principle, there's a lot one could talk about. For example, there's this 1,000-page book on Fourier infrared spectroscopy. We can also have a 1,000-page book on AFM, on ellipsometry, on Raman, on optics in general, nano-optics in particular. And now you don't have to worry. You don't have to read all of this, because we have the manual. Yeah, the direction is good, because that's obviously not possible. Yeah. And with this, I want to say a little bit. You cannot expect every detail to be explained somehow in the manual, or by us in particular, or by a certain group, one group. But instead, it's a really big community effort to figure out all these details, and they can be important. And also in near-field microscopy is no different. We have these details, and they can matter. If you don't take care of this, it's possible that you misinterpret your data. So that's a bit the problem. The good news is many things you can do without knowing every detail. Also, for far-field spectroscopy, there are many users. I don't think many of them know even the existence of this book. So you can make useful experiments either way. In the end, it's a trade-off. I think you shouldn't see this as a problem, these details, but more as a challenge, or as an opportunity. Because the more you know about these details, the more reliable you can extract information from the spectra. Yeah. And now the question is, which are the important details? And I don't have the answer for this, and it depends also on the application that you have. So if you study amide bands and how cancer affects the bands, you may have different problems and requirements than somebody working with polymers. So this is something that somehow the community has to define somehow. And for this, it's important to at least start documenting what you do in papers. Yeah. Okay. So I made this one claim that imaginary part of the permittivity, here this gray curve, it doesn't match far-field spectroscopy. Here is now shown. Yeah, so that's not a showstopper, I would say. And in fact, even if you compare different far-field techniques, ATR, FTIR, transmission FTIR, or grazing incidence FTIR, they all have different peak positions. And they also have different line widths, and they have even different peak shape. And even within one technique, you change, for example, the incidence angle, you again get a different peak position. So these are all details. Maybe you have to account for them. If you care about the absolute value, at which frequency is my peak, then you may have to consider these effects. And now I summarize a bit how this is in nano-FTIR. So here is from Stefan. He measured PMMA films of different thickness on silicon. And you can see here's one absorption peak in the phase. And as the layer gets thicker, the phase increases. The amplitude goes down because we see less of the substrate. But the phase peak, it just keeps going up. So the more material we have, the higher is the peak. That's relatively easy to understand. If we do the same with the nano-FTIR absorption, this is shown here. We increase the film thickness, signal goes up. We keep increasing the film thickness, and suddenly the peak goes down. So we don't anymore have the relation that more material gives a bigger peak, But for the nano-FTIR absorption, it's more complicated, because somehow the substrate plays also a role now when interpreting this. And then the next thing we can see, for thin films, the red curve here, we have a certain peak position, and for thick films, the black curve, we have a different peak position. So you have to compare it to other spectroscopy techniques. They will match the peak position. For the nano-FTIR phase, it's not so obvious. It looks like it stays the same. It also shifts slightly, but not so much. When looking at this table, which one of these two quantities seems easier to interpret? To me, I think the phase is easier to interpret. This is why I use it. Yeah, just because I understand better what's going on. And then here it's also summarized. The film thickness is plotted here, and this is the peak position. You can see for the nano-FTIR phase, within two wave numbers, it's constant, whereas for the nano-FTIR absorption, it does depend on the thickness much more. This also depends on the substrate. Yeah, I will mention how to deal with this in general later. So here I have just two examples. We've seen already this TMV. It's a very thin sample. Here is now compared with grazing incidence and transmission FTIR. We can nicely see a nano-FTIR looks like grazing incidence for thin films. And for the purple membrane sample here, it's also again an amide band. We can see this also matches grazing incidence FTIR. So for thin films on reflective substrates, this is a correlation you can easily make. Yeah. Now if you look closely, you don't have to look too closely actually, you see that here we have the amide 1 band and amide 2 band. And even though we have the same kind of material, in this sample, we see only one of the peaks. So what happened to the other one? It's definitely in here. So if you measure this with far field, you know there's two peaks in there. Or if you measure this in solution, let's say you know there's two peaks in here. But here we see only one. And then the question is why? And what you find when looking into literature, you find nano-FTIR probes preferentially bonds that are vertically oriented. I tried to trace a proof of this or explanation for this, and you don't find it. It's just people copying from each other. Not limited to s-SNOM community, also for TERS, you can find the same. And the explanation here, what's going on is we have, in this membrane, we have a protein which is going through the membrane, so it's very well oriented and perpendicular to the surface. And there's a CO double bond here, that is the amide 1 band, oscillating in this direction, so it's vertical, we can probe it. This other peak, the amide 2 band, which we don't see here, this is actually also oriented vertically, but the vibration is now in the plane. So it's just a different mode of vibration. So what matters is not really the orientation of the bond, but the orientation in which the vibration takes place. Or to be precise, the change of the dipole moment. Yeah, so we can see there's some dependence on the orientation of molecules, and this can actually be exploited to determine the molecular orientation. This was done here by Markus Raschke's group. They had an organic crystal, so it's very well aligned. And the molecule looks like this. So it has here this red vibrations. It's in the molecular plane. And then some blue vibrations, they are out of the molecular plane. And if you put now this molecule flat onto a substrate, what we would expect to probe only the vibrations out of the plane, which are these three here. So we can see them, and the other one, the red ones, they are kind of suppressed. By rotating the molecule or looking at a different crystal, it's now the opposite way. So the blue ones, they are now parallel to the sample. We don't see them strongly, and whereas the other peak turned on. So this is now an on-off experiment. We haven't gained much yet, but what this paper is about is to really have arbitrary orientation of molecules And then you can see for a specific peak how does it depend on the orientation angle. And then even extract from a nano-FTIR spectrum what is the orientation of the molecule. So this was mapped here. At every pixel, there was a nano-FTIR spectrum taken. And then from comparing model and experiment, you can determine the orientation angle. Yeah, we're still missing somehow an explanation what's going on here. And for this, you can calculate with a dipole, with a point dipole over a silicon substrate. You can calculate the electric fields that take place. And this is shown here as red. So red means it's a very high electric field perpendicular to the sample surface. So if we have a vibration in this direction, we can easily excite it and see it. But the in-plane field, this is actually 0 at the sample surface, or close to 0 here. For a perfect metal, it's really 0. And if you now put a molecule in here that's oriented in the plane, there's no electric field that can couple to this vibration. And that's why you cannot see it. That's why on the purple membrane sample, the peak was not here. A more intuitive way to explain this is to think about the field lines. So electric field is perpendicular on a reflective surface. And then it means you can only probe out of plane, not in plane. And this is known from far field spectroscopy as selection rule. So this you can actually find in this big red book. They have a chapter on selection rule. And the same applies now to nano-FTIR. And we don't need here any tip. So this calculation, it doesn't include an elongated tip. So that's not the reason why we have this. Okay. So to make a kind of intermediate summary, I have here a data set of spectra, different nano-FTIR spectra. And you can see there's a trend. Yeah? So this peak, somehow it's getting smaller. And I would like to know from you what could explain this behavior. And there are many different possible explanations. Or let's say you measure this in the lab. You have to explain this now.
Interface reflections.
Interface reflections, yeah. Yeah, could be. Yeah. So it could be something like varying thickness. Yeah, and you have an interface between the film and the substrate. This could happen. Molecular orientation, we've seen already. But there could be more reasons. What else could happen?
Birefringence.
Maybe. Yeah, birefringence. Yeah, I put this here. Could be birefringence. Could be chemical interaction. Could be that the sample degrades over time. Could be many things. And all these ideas, they are good. From this data alone, we don't get the answer. So you can interpret this in many ways, and you should. You should find different possibilities to explain your data and then rule out one by one which one makes sense. Yeah. So this is actually something, an experiment that we have done. We have looked at, so this is the data from before. It was PMMA layers of different thickness. But we also have a PMMA layer at different depths. And we can see this peak is also getting smaller. So if you plot them next to each other, they look the same. If you look from far away, then you start analyzing more in detail, you can start seeing, oh, the peak position is slightly different. Maybe the peak shape is also a bit different. So you can start untangling this and get more information from your sample, from your data. And in this case, I don't go into too much detail on this. There's indeed some interface reflections. This is all described by the multilayer reflection coefficient, which is this beta as a function of momentum. And I have one slide for people who know already what this is, or also more general. So these multilayer reflections, they happen also in the far field spectroscopy, where essentially some part of the light is absorbed in the layer, some part of it is reflected, and in general it's mixed. And that's why peak position can change, because you're mixing absorption and reflection. And exactly the same, I think, happens also in near fields.
And now you would describe this with this multi-layer reflection coefficient. In the far field, this depends also on the angle of incidence, which can be described by this Q. It's just the in-plane momentum. And for near fields, we also have this in-plane momentum. This is now not the angle of incidence, but it's more or less how confined is the wave. So a very large Q is a very strongly confined wave. Here there would be no interface reflection. And for a small Q, you would see some multiple reflections. I'll leave it at that. Story is not complete like this, but I think there's a lot of literature on this. If you want to model or reconstruct even the depth, these are some related papers. One brief advertisement I want to make is personal advertisement from the group in Manchester, from Jessica Boland and Tom Vincent, because they are working on s-SNOM, which is a Python package with the implemented finite dipole model and point dipole model. And the idea is that this will be published and made available for use, so that not everybody has to implement their own script. So it's a work in progress, but it's coming soon. Yeah, for organic samples, one last comment. It's very common to observe a kind of negative phase. Edith will talk more about that after a short break. Yeah, I just leave it at that. So for organic samples, we've seen they are weak oscillators. Permittivity, far field, near field, they all look quite similar at first sight, but if you look into more detail, you can see multi-layer reflections. There's dependence on orientation angle. Yeah. And I think the main takeaway is the near fields, they are not something exotic. They behave quite similar to far field reflections if you look closely, if you track it down. Okay. Are there any, so this is about the organic samples. So we make a short slot for questions here.
Back to the PMMA wedge experiment that you made. Does it matter whether you illuminate, let's say, along the wedge or perpendicular to that? So you can turn the wedge 90 degrees in your setup, do the same experiment, retrieve your data, and luckily get the same thing.
It can make a difference, and I'll show it in half an hour.
Okay.
It's about indirect illumination. Yeah, it can play a role, but doesn't always.
Lars, do you have a simple explanation why the optical contrast, let's say in the phase, it's stronger in the higher harmonics compared to the O1, for example?
Not really.
Not a simple explanation, right?
No.
Okay.
I can try and actually answer in this. So my simple explanation, well, relatively simple, would be that harmonics are kind of a measure of nonlinearity in your tip sample distance, right? So higher harmonics are more nonlinear, so they pick up the rate of change of the force with distance, right? So higher harmonic relates to higher nonlinearity. It's like the slope, you're measuring the slope. So the first harmonic, it's not exactly true, it's not one-to-one, yeah? But it's kind of, you can think about the first harmonic as the slope, the second harmonic is the second derivative, third derivative, and so on. And because higher harmonic relates to kind of higher derivative, you have stronger change, which results in the higher contrast. I don't know if this makes sense, but yeah, I tried.
Yeah, thanks for the very nice talk. You mentioned selection rule. Did you try maybe to use the tip and not put it on your sample, but on your side, where when your electrostatic field is then pointing like in that direction? Then you should can excite from the side the sample, and then you get like kind of an selection rule probe of such a near field signal.
I think in this case, if you have a dipole in the tip and next to it a dipole in the film, it's the other way around, and I think they cancel. It's a dipole-dipole interaction. It could depend on the permittivity, but okay, I think then I continue. So before we talked about weak oscillators, now I want to talk about strong oscillators. And all we have to do is make the oscillator stronger. So I have a parameter here, which, if you look here on the scale, this is now getting bigger, and also this will be bigger. And then you can see what happens to the nano-FTIR spectrum. So it's already stronger, and I would say not much has changed. We can make it even stronger. Let's see how far I have to go. I think I have to decrease this. Yeah, so now permittivity is almost reaching 0. We can see already it's somehow asymmetric. So something is changing from the shape already. So we don't anymore have this one-to-one correspondence as before. But we can make it even stronger. And now we have the situation where the permittivity is -1. This was mentioned already many times this week. And what happens now is that the amplitude signal is getting really large. There's this resonant tip-sample coupling. This is now, there's a damping, yeah, so the absorption is quite high. I think I can make it a bit smaller. And now we really start to see a really sharp peak. It's also now more reflective than gold. And all I did was make this weak oscillator strong. So it's the same thing, but it behaves differently. And are there already questions so far? No. And now what we can see, if I change the wavelengths, we will see a very strong contrast also in the s-SNOM amplitude. So now we are here. Now it's very dark. We can go closer to the resonance. Now it's very, very bright. It's even out of the color scale of the script. We can go even a bit more. There's a place where the permittivity reaches 1. There's no real reflection happening here anymore. So that's why it's really, really dark. It's very hard to get any near-field signal from this region. Yeah, so this is how it looks in theory. We can see how it looks in the experiment or in the literature. And this is actually the earliest s-SNOM experiments. They were made on, a lot of them were made on this kind of samples, like silicon carbide, for example. We've seen this example before. This is a dielectric function. We can see here the oscillator. It's very strong, so the epsilon gets negative. Here we see epsilon is around -1, -2, and the near-field signal is very large. And we've seen this also before. We can image this, we can take a spectrum of this. It's very strong signals. And in principle, this is the chemical identity of the silicon carbide, you can say, because it's the phonon. And here in this experiment, it's normalized to gold. We can see that the signal is 10 times higher than gold. So we have 10 times more signal, which means we have really good signal to noise. And we can make very sensitive measurements using this, exploiting this phonon resonance. And this is done, for example, here. This is, again, silicon carbide, measured at one of these resonances. And we can see a very sharp contrast here, even though it's both silicon carbide. But it's just a different crystal structure in one of the areas. So the phonon is slightly shifted, slightly more damped. And we can nicely map this with s-SNOM in amplitude and phase. So we can identify crystal polytypes via the phonon. This was the example on the left. We can also see radiation damage. For example, when implanting ions into a crystal lattice, the crystal lattice will be damaged, which weakens the phonon resonance. And this can be imaged. This can be seen in spectra. The more dopants we use, the more we damage our phonon. And we can image this. We can tune the laser to this very sharp phonon resonance. And this phonon can be affected by strain. And this is now mapped here. So it's using the s-SNOM to map strain in a phonon, in a semiconductor, by exploiting this super high sensitivity that we have for this kind of samples. And I think exploiting this kind of effect, there's still a lot that one could analyze, because the sensitivity is just so high. And one thing that's quite important for this kind of samples. So we always say it's a resonant response. Sasha already mentioned it's not the beta that's resonant, but you have to take into account the tip and the sample. So it's a resonant system. It's there together, which means if the tip is further away from the sample, you modify this resonance. So this resonance it can be shifted, and this is shown here in a calculation for different heights of the tip. This resonance is shifted, and this is because it's we say resonant tip sample interaction, but really what we should say is tip plus sample interaction, and then it's this alpha effective is what's resonant. Yeah. This also works in the experiment, so we can see here that this resonance is shifted. And one consequence of this is also, because this is a height-dependent effect, this means also that demodulation affects this and tapping amplitude affects this. Whenever there's a height dependence, you could look at different harmonics and see how are they affected differently, which is shown here. These are now only calculations of the silicon carbide resonance, this phonon here, 4 different tapping amplitudes. And they look very differently. So if you put a different tapping amplitude during the measurement, you need to account for this also in your calculation. So, and that's why it's important for this kind of samples, especially, keep the experimental parameters constant. Okay, so these were phonons. Are there any urgent questions already about phonons?
It's clear that we cannot use infrared libraries for identification of inorganic materials, classical infrared spectra to identify based on the nano-FTIR signature of such materials. But is it a possibility to make a library of nano-FTIR spectra for such inorganic materials? Do you think this is possible?
Yeah, if you define what tip you use, what tapping amplitude, what demodulation order, okay. Maybe, yeah.
So this could be maybe a challenge for community. If people working in FTIR spectroscopy could make a library for materials, maybe nano-FTIR community could also make a library for inorganic materials. But I agree, we need to have some standard parameters like tapping amplitude, then maybe this is possible,
yeah.
Right?
Yeah. Or one would calculate and create a library from that as a starting point.
Okay.
Yeah.
Thanks.
Okay. So, there was one more question.
Hi. Maybe I shouldn't even use a microphone for this question because probably I'm the only one in the audience who actually asked this. But when you say the word phonon, you are not considering any nonlinear polarization, right? You just assume that at this certain wavelengths or optical frequency, you will have some absorption, right? And in this how your linear dielectric function should look, considering this effect.
I'm not sure what. So I say phonon, but really what I have in the back of my mind is the dielectric function. So I don't know if anything is. I don't know what's causing this. If anything is nonlinear or so. This I don't know.
Right. So, but at the back of your head, what you probably assume, or what I would assume, is that this actually material absorbs, right, at this frequency, which manifests itself in the dielectric function of such a shape.
It absorbs. Actually, I skipped this on one of the slides. So yeah, it absorbs a lot, but what normally is probed is the far field reflectivity. You see the Reststrahlen band. So it reflects. To characterize a phonon, you would look at the reflectivity, and this is how they are, as I understand, how they are characterized.
Thank you.
Yeah, very good question. I would like to comment on this. So I think you mean with linearity, you mean the polarizability or the permittivity function. So that's not a nonlinear effect. So this is all described by the purely linear dielectric function. That's the one thing that I want to say here. The other thing is that Lars, if you show the spectrum again, so we have, this is a polar crystal, and that's what we need. So we need an optical active phonon, and then we have the Räth-Strahlen band between the transverse optical and the longitudinal optical phonon. So these are phonons, okay? Now the peak appears where epsilon here is roughly -1, -2, right? That's neither L or nor TO phonon, so it's in between. And this resonance occurs because beta is epsilon -1 divided by epsilon +1, right? So this diverges where epsilon is -1. And that is the dispersion limit for surface phonon polaritons. So these are surface waves that can propagate on a material that has a negative permittivity. This is similar to the surface plasmon polariton that is very well known in the visible spectral range. So in the mid-infrared, we have it's the same phenomena. Epsilon is negative, but it's a phonon polariton. And as it's on the surface, it's a surface phonon polariton, okay? That's the one thing. And then these polaritons have a dispersion, and this dispersion reaches from TO to the SO, the surface optical phonon frequency, and that is exactly where epsilon is -1, like for the surface plasmon polariton. So that's the dispersion limit where this resonance occurs in beta. Because here the density of surface states diverges, and now the near fields have a lot of density or lots of states in which they can couple into. And what the tip is doing, it excites resonantly a surface phonon polariton. Now, in principle, these guys could propagate away, and this is what we see on HBN, on graphene, and so on. But these are very thin layers where we see that, and the wavelength is on the scale of the tip radius. And for that reason, there's a very good momentum matching between the near fields and the surface waves, and that's why the tip launches these waves, and we see them. Now, in this case, that was a bulk surface, and on a bulk surface, the surface phonon polariton at this frequency is roughly half the photon wavelength. So now the tips near field are so concentrated that the momentum mismatch between the propagating surface mode is very large. And for that reason, we have a resonant interaction, but it's purely quasi-electrostatic, and so a surface wave is not propagating away. But so the real reason is that we excite resonantly a surface phonon polariton mode, which is a non-propagating one, which one could actually nicely see in a numerical simulation that you probably don't have here, no?
No.
So it's really, you excite this mode, it's just the momentum mismatch is so big that it does not propagate away. So that when we saw this for the first time, we were discussing this for years, what is going on there. We never understood it, but now with the 2D materials, which are very thin, you can prove it actually, because now these guys really start to propagate away. If the layer becomes thin and the dispersion becomes such that these wavelengths of these modes becomes comparable to the tip size. So not sure whether.
Thank you.
So we have one more class of interaction with material, which is charge carrier response or Drude response. And I would like you to take a look briefly at this shape here of this dielectric function. It's just this curve going from negative values to positive. And now what I do, I make this very small, this oscillator. I just turn it off. It should be, this was, it's very small. And I turn on charge carriers. And here I have to play around with essentially the charge carrier concentration and the damping. So let's make the damping small. We want a good material, maybe even smaller. Yeah, this is good. And we can see more or less the same shape as we had before, which also means we crossed at some point -1. We have a very strongly enhanced near field response. And this is how a charge carriers look like in nano-FTIR. This is now a very good conductor. If we increase a bit the damping, we make the properties a bit worse. That's the wrong, sorry. We need this one. Now we see for very low frequencies, we observe a higher reflectivity, and for high frequencies, we observe low reflectivity. And this is comparable to a far field measurement, where if you are above the plasma frequency, which is now this faint line, above the plasma frequency, the sample transmits the light. And we can now increase the charge carrier concentration, and then this transition from highly reflective to weakly reflective is moving to higher frequencies. And this is why we can indeed in the s-SNOM measure different charge carrier concentrations. Here on the right is essentially described what we have just seen. For high frequencies, sample is not reflecting. For low frequencies, it's very reflecting. And this transition depends on the charge carrier concentration. And now, all we have to do to find out, to quantify the charge carrier concentration is where is this transition? And this is a really broad spectral range that we're now talking about. This is from the terahertz to the infrared range and maybe even the visible. But it's possible to map out this transition. So for example, here in terahertz, or let's highlight one of these curves. For this doping, at low frequencies, at terahertz, we observe, we expect high reflectivity, which is what we see here on this field. It's very bright. In the infrared range, we would be somewhere here. Low reflectivity, that's exactly what we see in this image here. And like this, we know very roughly, we have 10 to the power of 19 centimeter cubed, inverse cubed, of charge carriers. Here is plotted only the amplitude. We also have the phase. This would then relate to the damping of the charge carriers. Still, you have to use the finite dipole model to properly fit this and extract a real number. And this on the left is the same plot as before. There's a second very important plot for any charge carriers, if you want to image them in s-SNOM, which is at a fixed wavelength. How does it look when the sample has different charge carriers? Because if you have a QCL laser, the wavelength is fixed. You don't have this spectrum, but you have fixed wavelength, and different areas of the sample, they will light up differently strong, as shown here. And again, we can see that for the low frequencies, for terahertz, some areas, like this one, is reflecting. But for infrared frequencies, for much higher frequencies, we are suddenly here, and it's turning dark. And so, and even there's a small dark stripe here at 10 to the power of 17. It's very hard to see. This corresponds here to the dip roughly. So, and this is why we can write here the values, at least order of magnitude, of charge carrier concentration. So we can map this. And one example from Thomas, he was kind enough to send us the slides, so I wanted to include this here, is the indium arsenide nanowire. And you can see here, this is topography, I think overlapped with the optical amplitude. There's some variation along the nanowire. This is caused by the way they grow, this nanowire. It's grown standing up, and then as it's growing, they change somehow the environment or temperature, and then charge carrier concentration is different. And we can see this with the s-SNOM. And as motivated before, we can do this for many different frequencies, and we can see how this contrast evolves. Let's go from here. At very high frequency, it's not reflective. But at lower frequency, it starts becoming reflective. So this means very likely there's a charge carrier response here. And the point where this turns on, the contrast, is different. So here, we see already something here, but at a different nanowire position, contrast turns on here. So the charge carrier concentration will be lower here compared to here on the wire. It's very abstract, but what you can do is take a line profile of this nanowire, so that you have at every pixel a spectrum, and then use the finite dipole model to make a fit, where the fit parameters are charge carrier concentration and mobility, essentially, of the sample. And then the fit parameters that best describe the experiment, this is now the charge carrier concentration where we say that's what we have in the sample. And it's actually surprisingly accurate. So this is, I mean, this was done with a QCL laser, so experiment is tricky, but still accuracy is on the order of 5%, so the error bar is quite small. But I must say that this depends also how well does your model fit to the physics that's happening in your sample. So we make, of course, here many simplifications, that this is a semi-infinite sample of free charge carrier response. The only addition that was made here is as the charge carrier density increases, also the mobility goes down, just because there's more electron interaction. And this you can include, for example, via effective mass. Yeah. Okay. So with this, I'm at the end of this part. In summary, I just show this graph where we started. And I hope that between the first time and now seeing this graph, you can fill it with a little bit more life. So if you see here, for example, what we have just talked about, this black curve, this turn is characteristic of charge carriers. And we know that they are reflective at low frequencies. This is more or less what's illustrated here. Then we have seen in the beginning weak oscillators. This shape here of the peaks is the same for permittivity and for near field. It's relatively easy. And by making this oscillator stronger, we have this here, which describes like phonons. You can see that the peak becomes a bit asymmetric, but it's also very strong, which we can maybe exploit. Yeah, and actually this graph is something that we came up very recently, and I think if you understand this graph, then you understand already quite a lot, and it helps a lot in interpreting experimental data. Yeah, with this I'm at the end of this.
Next speaker is still Lars, but let's check
after the break.
Yeah, if there are other questions before we move on. Yeah, one there.
Yes, thank you. I was wondering, can you maybe comment on what influence the tip dimension could have on these different type of oscillators? Have you had any experience with that?
Yeah. So for the phonons, it can have a very strong effect because it's a resonance between tip and sample. So they're both together. If you change the tip, you change the response. The same is for charge carriers if they are very weakly damped, because then you also have the strong tip-sample coupling. Otherwise, it changes, mostly I would say the height of the peaks. So you get different numbers, the same way that you get different numbers if you have different tapping amplitude or different demodulation order. Yeah.
Thank you.
Thank you, Lars, for a nice talk. Everything is so far clear if we assume isotropic systems. Mm-hmm. That means we have no, let's say, no birefringence or something, and the coupling of your adsorbate, whatever you have, to your substrate is always no worry about. So now, can you comment or sketch any kind of procedure or way how to go on if there's some isotropy there, anisotropy there?
There is a poster by Isabel, right? Or? No, it's not. No poster. It's a work in progress. Yeah, it's a work in progress. So we have to take this into account. In the break, I think. Yeah, because it's now work that I'm not anymore doing. I don't want to disclose too much. Yeah.
Okay, maybe if there are no other questions, let's move to the next topic that is more about the ratio between harmonics, right? So it's next 15 minutes.
I think we may take a small break.